STAT340 Week 8. The following video was actually recorded in 2022 where the topics were given in a slightly different order. I have tried to annotate this during the video. Also, the R package, which is referred to called STAT340, is exactly the same R package that we call bias data this year. So the content of today's topic or lecture is mixed models. And I have to say a few words first about what is mixed models and dependencies in data, because that's what we are sort of dealing with here now. A little bit about how we can plot data to reveal this dependency. And then the random effects. Random effects. This is what we are sort of introducing now. And there are some notation and stuff that we have to talk a little bit about. And this week I will focus on pseudo-replication, models to deal with pseudo-replication. And next week we will also talk about mixed models, and then we will focus on something else. But this week this is the sort of main issue. Longitudinal data, that means temporal pseudo-replication as we call it. It means that we measure the same object over time. And random intercept, random slope type of models. That's what we will look at this week. I will also say a few words about how we fit the mixed models, because this has some implication for how we compare models. Because variable selection or model selection is also on the agenda here, like we have seen before. So a little bit on that at the end here. But as I said, mixed models is the big topic, and this is mostly from chapter 19 in the R book. I would also say that mixed model is used quite a lot. Whenever you do experiments, or if you collect data elsewhere without sort of controlled experiments, mixed models are very frequently used to analyze data. So it's quite likely that you will come across this in your projects. And I know that there are many sort of experts of mixed models at NMBU among the sort of experimentalists. So what you get here now is just an introduction to this topic, right? And it's more than likely that if you are sort of studying a specific field of science, there are sort of more specialized mixed models for that research field, right? Like animal sciences or natural, the different departments or faculties at NMBU, there are users of mixed models that can sort of teach you more specific models. But we will look at some general introduction. So what is mixed models really? If you go back to the beginning of this course, we looked at linear models, right? Of this type, this is a regression model where we typically have some continuous or numerical quantitative variables, right? And we want to fit, and we have a response variable over here, which is also quantitative and continuous. And then we fit this regression model, and we have an error term here. We called it an error term or residuals, right? Because we know that the data doesn't fit exactly this model, so this is the explanation for that. Or we looked at ANOVA models of this type, which is written. Then we have no sort of x's anymore, right? We have only the factors, right? These are factors with different levels. So I and j indicate level number I here, level number b here, j here. But again, the response here is continuous, and we have factors instead. And we saw that we could even combine these two, right? So we could have regression models with some factors. what we call analysis of covariance. What is common to these models is that they all have this sort of stochastic element at the end here. So in all cases, we assume that this random variable, E, that we call it here, is normal distributed like this with zero expectation and some unknown variance or standard deviation. And we also assumed they were independent, right? Independent and identically distributed is usually shorted like this, IID. This is the fundamental assumption of these models here. Regression, standard regression and standard ANOVA models. And actually, we can tolerate quite some deviations from the normal distribution. And we can still use this model and their theory with success. So even if we assume normal distribution of the errors, this is not sort of dramatically important. If you have severe deviations, it's important, but we can tolerate quite some deviations from the normal distribution, and still these are valid. I mean, so we could make these diagnostic plots and so on and so on. But what if the data are not independent? This can really be a severe violation. So if the independence assumption breaks down, these models can really give you the wrong answer. So you could say that among these assumptions we made, the independence is perhaps the most important one. And this one we haven't really talked about until now. What do we do if this one breaks down? That's what we are going to look at now. So what we are looking at now, at least in both this week and next, are still linear models of this type here. And we will still assume we have a response of the similar type as we had here, but we will make some extension to this part of the model, you could say, this part of the model. So these parts here will not change in a sense, but this part will. And if you remember back to before Easter, you talked about generalized linear models, and that was for different responses, right? Where you had either a binary response and you used logistic regression, or you had counts and you used Poisson regression. What I'm talking about here in mixed model may also be combined with those type of responses. But for our course now here in STAT340, we will only consider continuous responses here for our mixed models. But I mention it now right away, there is no sort of limitation. It's not limited to that setting. It's only that we will only discuss it in that setting. You could use mixed models with Poisson regression, for instance. It's possible. Okay. We typically use mixed models to deal with dependency in the data. So that's how we deal with dependency. If we don't have independent data for some reason, this is one way we can deal with this. And in mixed models, or what we call random effects models, we will specify that shortly. What is typical is you have more than one stochastic term. Notice from the previous slide, the models we looked at had one stochastic term, the E, that we added in the end. So what is different now? We will have more than one stochastic term that sort of describes the variation in our data. So here we have an example of a mixed model. This is a mixed model, and it's sort of a regression type of model. And here you can see we have the E as before, which is assumed to be normal distributed with zero expectation and some standard deviation. But we also have another term here, which is also normal distributed with expectancy 0 and with some other, just a different standard deviation. So instead of having sort of one error term, we now have two. And what is to be gained by this? We will see. And notice that this part, this is just a sort of a simple regression model, right? It's not a sort of affected by this. So the variance in our response variable here is now a combination of two or more random variables. In this case, two, but it could be more. It's a combination of two. So in this example above, we have some fixed effects, as we call it, and that's the first part here, right? We have some parameters, the intercept and the slope. This is we have seen before, right? But now we have random effects A and random effect E, and both have also parameters, right? Here. So we have actually four parameters in this model then. Two fixed, two sort of regression coefficients, plus two standard deviations. And a mixed model has both fixed and random effects, and more than one random effect then, right? Otherwise we don't call it. If this one was lacking, we are sort of, then we have standard regression model, right? Which we may call a fixed model instead of a mixed model. But typically we use the term mixed model when we have some fixed effects, but also more than one random effect. What is often called just a random effect model has actually no fixed effects, or actually one, the intercept is always there, but if you ignore the intercept, then it has no fixed effects, only random effects. And we will see some example of it next week. I will not dwell too much with the pure random effect models, as you can, and in my eyes they are sort of just specialization of the mixed models, right? So when I talk about mixed models, I also include these ones. But they are in the literature, you find this term random effect model, sort of meaning only these models where you have purely random effects. Okay. Dependency. So how can we actually detect if there are dependencies in our data? Well, it's not so easy, but in principle you could reason like this. Fit a model assuming independent data, for instance using LM, right, for the standard regression or ANOVA model, assuming independence, and then you compute the residuals, right, the observation minus the fitted value for each observation, or predicted as we call it. That's the residuals, right? And then if the data are truly independent and identically distributed, which is the assumption up here, right? Then there should be no structure in this residual. So it means that any random shuffling of the residuals should not alter the picture, right? So remember we did this diagnostic plot, so we looked at if the residuals have more or less the same variance along the fitted values, right? That's one way of looking for structure. Is the variance growing or shrinking? It should be the same all over, right? That's the part of the ID here, the identically distributed, right? But the independence also means that you can shuffle their order, right? You don't know which residual sort of belong to which observation. There should be no sort of, it shouldn't be possible to sort of detect that if the data are truly independent. This is of course not always a recipe to, I mean what we look for structure and how should we plot, and and how should we actually inspect the residuals. So this is in theory what you should do, but it's not always easy to do this in reality. What is important to remember is that in order to see this dependency, we need some information about how the data were collected, which these residuals, do we have any other information about them in order to see this structure, right? For instance, do some residuals come from some experimental units, right, in our data set, and do they group at one end of the plot or something like that? This type of information is really crucial in order to see if you have some dependency in your data. So never ask a statistician about this. Right? Are there dependencies in my data? Because it's not something that a statistician will sort of know or not know. This is something that the one who collected the data will tell you. The experimentalist has the information that you ask for now. This is not sort of statistics. This is about collecting data. Yeah, it's so. I mean, experimental design is, of course, also sort of a part of statistics, but my point is, don't go to the sort of statistics expert to ask about this. This is something you or those who collected the data must tell you or give you the information that you require. Let's have a short R session to have a look at this. Okay. Let's have a look at this reading data set. And I have started RStudio and I created myself a script here for week 11, right, in my STAT340 folder. So what is this data set? Let's copy from here. So let's save and run this step by step. The reading data is a tiny little data set just for illustration. So it's data about reading abilities with children at different ages, and these children have been taught reading in a sort of an alternative way. So one is probably interested in seeing if the reading ability is improving or not. Right, so we have age here and reading ability as a score here. I don't know how this score is created. It's not my data set, but it shouldn't be too difficult to follow this. Let's plot the data and fit some standard linear model like we have done before. So here I just load the tidyverse packages because I'm going to use it for plotting. Right, and then I make a simple plot of age on the x-axis versus reading ability on the y-axis. No strange thing about it, like this. So here are my 6 data points, right? This is all we have. And when you look at this picture here, it looks like there is a negative effect of reading ability of age, right? The larger the age, the older, the poorer the reading ability gets. And if you fit a mixed model here, assuming that all data are independent and normal distributed and blah blah blah, we also estimate exactly this, of course, right? So we have a negative slope here, right, of age. Negative slope, but you can see it's not significant. It's not significant. And that's because there's quite a big spread in the data, right? And only 6 data points. So this is not enough to, so even if we have 4 degrees of freedom, because we have an intercept and a slope, right? So we have 2 parameters. And we have 6 data points, so then we have 4 degrees of freedom left. 6 minus 2. So this is the conclusion from fitting the standard linear regression model to this dataset. However, there is another column in this table. If we click it open here, you will see that there is a third column here that we didn't use now, and that's called child. And this is information about how the data was collected. So this one indicates that the first two measurements come from the same child, child number 1. The next two measurements are also from the same child, child number 2, and this is child number 3. And we never used this information in the first model here now, right? Or in the plotting here. And that's exactly what we will do now. So let's plot this data again, but use this information. So let me try to put it in one page like this. So now, so what we do now, we plot the residuals. We plot the residuals of the model that we got up here, right? So I take the fitted values along the x-axis and then the residuals on the y-axis. And now I color the points with this child information. And then it looks like this. So here we have, this is one of these diagnostic plots we have seen before, right? Where we have the fitted values along the x-axis and the residuals along the y-axis. And we look for, is there a growing variance along this axis here, right? There should be approximately the same type of variance along. And with this only 6 points, it looks like the variance is more or less the same here, right? That's not the problem. The problem is, of course, when we color by child, we see there is a clear structure in these residuals because the blue ones are down here, the green ones in the middle, and the red ones are over here. And if this was truly independent data, then blue, red, and green should be sort of mixed in all ways, right? Both in this direction and in this direction. There should be no structure, right? But notice that this structure is only visible because we have this extra column so that we can color the points by, in this case, which child they are from. And then we see that this is not independent data in a sense. So we can actually plot the raw data in the same way, of course, like we did. So let me copy this one. So instead of plotting the residuals, we can go back and plot just like we did up here, right? X and Y. But we color with this child column. And then we, of course, see right away how this data are, right? So we can now see that these two measurements are on the same child, right? And we can see that as this child goes from 7 years of age to, from 6 to 7 years of age, the reading ability grows. So this child has been a better reader after 1 year. And this child also better after 1 year, and this child also better. So actually the reading ability improves here. But because these children are of different ages from the beginning, and actually the older children started out with the poorer reading abilities here, then when we had the first plot, right, and we didn't color by child, it looks like everything is going down. While in reality, it's quite opposite. Everything is going up once we have this information here. And this tiny little example is a nice one to illustrate how important it is to have this extra information about how the data were collected. That these two are from the same child, these two and these two. So, and these are not independent, right? There is a dependency here because once you have made the first measurement here, and if you now have the other ones, the other 5, data points to choose among if you didn't have any color, but you had this information. Once you know that this is the reading ability of child 1, then you will immediately guess that this is the second measurement of child 1. Not this one, or this one, or this one. Right? So, because the children tend to increase, right, in the reading abilities, and these two measurements are sort of linked together, and these two are linked together, and these two are linked together. They are not independent of each other because they are made on the same person. So this is how you can reveal dependency, by having some extra information, and try to make plots where you either use color like I did here, or as we will see later, some other way to sort of include as much information as possible about your data in the plot, and then start looking for structures. Is there anything that sort of relates some measurements together here? Or are all measurements just could be randomly shuffled? No, they cannot. Okay, so let's go back and have a look at random effect models. Well, not random effect models, but models with random effects, I should have said. So what is this? From week 2, we talked about regression with factors, analysis of covariance, or ANCOVA, right? The reading data could be used in this setting, where we have the reading ability here for child number I and time point number j. It's a regression model, right, where this is time, x is now the time point, and then we have a fixed effect, or a factor here indicating the effect of the different different children. So this one is separate. It's a factor with 3 levels, 1 for each of the 3 children, and then we have the stochastic term here. So this we saw already in week 2. We can just rearrange so that it becomes apparent that the intercept is now, we have a sort of a common intercept here, but then we have the intercept per child, right? So this is like fitting 3 regression lines, right? With the same slope, but with 3 different intercepts. And then this one is a normal distributed and blah 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 as before. 3 children and 2 time points for each child, right? So this should be familiar stuff. If you go back to week 2, we did something similar with some smoker or non-smoking mothers for the child, the weight of newborn children. The mixed model variant for the exact same data would typically look something like this. And notice it's not very different from the one up here. The only thing that it changes actually is that this alpha I here is replaced by a I here in my notation. And if you just rearrange again, we get exactly the same as up here. So now this is the intercept, right, for each child. And now this term is the same as before, or at least it has the same specification. But now this one is also a stochastic term. And it was not up here. Here it was a factor with 3 levels. Now it is sort of a factor with infinite many levels, where we have 3 of them in this data set. And you see here we now specify that this comes also from a normal distribution with some standard deviation unknown to us. So what is actually the difference between this ANCOVA model up here and the mixed model down here? What is the difference? Yeah, the fixed model, as I call this one, I call this a fixed model now, describes the data for these 3 children in particular. These 3 children here that we have in our data set are described here now. While the mixed model describes data for a population of children from which the 3 children we have now are randomly sampled. Can you see that? This describes sort of a bigger universe. Because this is a description not only of, this describes only for these 3 children how the data look like, but this model tries to also say something about all children. Because it says that these 3 children we have now are actually sampled from a normal distribution that describes all children. So it's sort of more ambitious. This is a more ambitious model in a sense. It tries to expand the conclusions that we draw to all children and not only to these 3 that we have in our current data set. I should say that if you are for some reason particularly interested in these 3 children, then this approach here is the one you should use. However, if these 3 children are in your mind not particularly interesting, they are just example of children, and you are more interested in the general conclusion about reading abilities for all children, then you should look at this model instead. We will come back to this. Variances and correlation. The mixed models, we estimate the variances, and now we have 2 of them, right? The 2 standard deviations in the model. And of course the variances are just the standard deviation squared, right? So the hat means we have now estimated them from data, right? And then this variance here, the sigma A hat squared, describes the variation now between the children, the random children, right? And we saw in the previous slide, it's sort of a random intercept. It means that the intercept has now an element of randomness in it. And this gives us some information about other children as well, not yet in our data. And this is the difference between the mixed model and the fixed model in the previous slide. Because the mixed model says something about all children, right? Because it assumes that the 3 children we now have are sampled from a normal distribution describing all children. While the fixed model does no such thing. It only describes these exact 3 children, and it says nothing about next child that you collect data for. It's completely decoupled, while the mixed model is not. It tries to sort of smooth the information to also apply to the next child that you collect data for. This one here describes then, of course, the variation within each variation in the data within each child after you have sort of subtracted the fixed effect then. So it's actually the variation in the residuals from each child, not the variation in the data. It should have been residuals here, because there is of course a substantial variation in the data because of the time effect, right? The fixed effect, the fixed effect over time, the age. So the fraction here, if you take this variance and divide by the sum of the 2, and we call it with the Greek letter rho here, this is what we call the correlation between the measurements from the same child. It's actually the correlation between the measurements from the same child. And then you can see that if this is close to 0, it means that this variance is small compared to this variance here. Right? If this one is a small value and this is a big one, then this fraction comes close to 0. Then we can actually skip the whole random effect in our model, because it explain very little of the total variation. So we have an ignorable dependency, right? A very small correlation between measurements on the same child. But on the other hand, if this one is big compared to this one, then this comes close to 1, right? Then there's a huge correlation between measurements on the same child. And then we should definitely not skip the random effect. So this is how this random effect of child, in this case, can reveal the dependency in our data. If we fit the model, assuming there is a random effect of child, and if this, and you get an estimate for this one, you get an estimate for this one, and you compare these two, actually by computing this fraction here, and if this is close to 1, then you know that this random effect was important. It was important to include this in our model. If it's close to 0, well, it didn't help us much, right? We can ignore it and just use the standard regression model again. So that's what you can obtain by looking at these variances here. And that's something you should always do. We will see that in a minute. Just a few words about notation here. And I included this picture because it's sort of a funny. This was from a Christmas party many years ago where we actually had this. It says here in Norwegian that parameters should be written with Greek letters and variables with Latin letters. And that's exactly what I want to tell you now. To make things simpler, I mean, this is just to make things simpler. Be consistent in notation. Because everything is so much simpler if you don't have to worry about this as well. And this is what I try to stick to this rule consistently. And if you happen to find some on my lecture notes or whatever where I don't, please tell me, because I would really like to stick to this rule. Always use Greek letters for parameters. And what are parameters? They are regression coefficients, so that's why we use the Greek betas. I don't know why beta is used, but that's a convention, I think. Or the fixed effects in ANOVA models or ANCOVA models, mu, alpha, tau, whatever, Greek letters, right? Or the standard deviations, and that's sigma with some subscript usually, right? All these are parameters, and therefore I tried always to use Greek letters. On the other hand, if you have variables, random variables or fixed variables, we use the ordinary Latin letters. So, for instance, the predictor variable is always called y, and predictor variables are typically called x, and these are ordinary letters, right? Random effects, I try to always use A, B, C, and so, except for this error term that we saw from the first day. It's by convention called E. And this is unfortunately not always done in the literature. It's sort of confusing this. First of all, this one is often referred to as epsilon, which is a Greek letter, so it shouldn't, because this is not a random, this is not a parameter, right? This is a random variable. So it shouldn't be called epsilon, it should be called E. And the same with the random effects are also used Greek letters for those in the literature. And I mean, it's not illegal, of course, right? But it adds confusion, right? So if you see a model, you don't know, is this effect a fixed or a random effect? You have to specify that, right? But if you use this rule here, it sort of becomes apparent immediately. I think this is a nice rule to stick to. Okay. Yeah, we will talk more about indexing next week, because we have this indexing, right? Yeah, that is also some rules there, but we will be a little bit sloppy in that term now, but we will look more at that next week into the indexing. It has to do with what we call nested versus crossed data. So let's go back to R and have a look at the reading data and fit a mixed model. Well, let's have a look at this reading data again and fit a mixed model. First of all, let's specify the mixed model, and this is exactly the same as we saw in the lecture notes, right? Where we have the reading ability as a response. Then we have sort of a regression model here where X is now the age of child I, age number J, right? Because there are 2 ages for every child, right? So I goes 1, 2, 3, J goes 1, 2. So this is the sort of regression line, you could say. And then we have the random effect here, which is a random effect for each child. And this now sort of influences the intercept. And why is that? If you take a look at the data, this is reasonable, right? If you look at the data from the previous session here, we plotted them, right? So now we can see which data comes from each child. It looks like the slope is more or less the same for these children. It's not a big, it's not sort of a child, it's not a slope per child. At least that's not very visible here. What is very per child is the intercept. If you imagine a regression line through these 2 red here, and draw it back to age equals 0, you have the intercept, right? And then you will see that this line has a different intercept and this one has a different. So they are sort of 3 more or less parallel regression lines, but having different intercepts. And that's why we put the random effect on the intercept here now, right? So what separates the 3 children is the intercepts. And we say that this is a random intercept model. So let's fit this random intercept model. How do we do it? Here is the code for doing it. So let me copy it into here. And first of all, in order to fit mixed models in R, you need to have some R packages. Either this one, NLME, or another one called LME4. We will see that next week, actually. So this week we will only use this. So you have to install this R package here. It's not part of the base packages. I have done that. It's straightforward. You just install packages like you will normally do. You find it at Kran. So let me just load this package. And then here is how you fit a mixed model using this package. First of all, in general, you can see that this is not very different from the LM function that we have used before. The function is called LME. Almost the same name. Again, we specify the response here, and we use this tilde operator, and then we specify the rest of the model, the predictors, you could say here. And then there is something which is different from the LM, because here we specify the random effects. The random effects. You use the word random equals, and then you can see there is again this formula, as we call it, with this tilde operator. And this is a little bit special notation. So what do we mean here? Well, it means when we say tilde 1, it means the random effect should affect the intercept. The 1 means the intercept. And then you have this vertical bar here. You need to locate that on your keyboard. Where do you have this character here? To my keyboard, it's the upper left key in my keyboard. And then you specify the factor. This must be a factor, right? The factor that groups the observations by the way you want to group them, right? So that the observations that are from the same group are now sort of dependent of each other. Right? So this is where the sort of dependency information comes into the model. You say that for each new child, sample 1 random effect and add that to the intercept. That's how you can read this. For each new level of this factor, SAMP1 normal distributed value and add that to the intercept. And then you specify which table the data come from and so on. So that's the same as before. Let's fit this model now. Like that. And then we can, of course, as we have done before, look at the summary of such a fitted object. Let's do that. And let me increase the size of the, yeah. So let's have a small look at the output from this one, because it deviates a little bit from the LM output, but not that much either. First of all, it says linear mixed effect model fitted with REML. We will come back to that. What does this mean? And here we have, we recognize this AIC, Akaike's information criterion. If you go back to like week 2, I think we talked about this, and we will come back to that later today. This is a criterion that tells us a little bit about how well this model fits the data, in a sense. Yeah, so there's a value here. But this is for comparing against other models. So the value in itself carries no information. Is 18.6, is that a small or big value? Impossible to say, because this one grows with the number of data and the type of model. So it's only for comparing against some alternative model, you could say. Yeah, we will come back to that. Here is the random effects now. And yeah, first it says just the formula we used, and here comes now the standard deviations. These are the standard deviations, right? So this is the sigma A, hat actually, the estimate of it, and this is the sigma E from our formula, right? So so this one has a standard deviation, and this one has a standard deviation. And this one is the first one, right? And we can see this is quite big compared to the second one. Can you see that? And remember from the lecture, I said that we can compute this correlation rho as, what should it be? It should be this sigma A, and that's this one, right? So let me copy that now down here. 2 points divided by the sum of this one plus the sigma E, right? Copy, and actually what I haven't done, I should square this, right? Because it should be the variances, right? So this one should be squared, this one should be squared, and this one should be squared. And now we can compute the rho here. And it's super big, right? This is almost 1. This is almost 1. So it means that in this case we have a super strong correlation between the measurements on the same child. And that's not so strange, right? When we see this picture here. Then we have the fixed effects, and this is more like the same as we have seen before, right? So this is now the intercept, the beta 0, and this is the beta 1, the regression coefficients for age, right? And this is similar to the output from LM actually, with the coefficient itself here, its standard error here, degrees of freedom, and notice this is only 2 degrees of freedom now because we have used more parameters, right? We have only sort of, yeah, we have only the 2 regression coefficients, but we have the standard deviations of the random effects now. We get a t-value here and a corresponding p-value here. And that's actually, and the rest here, the correlation here, that's not so important for us now. You can actually see the number of observations here, 6, yeah, and there are grouping. There are 3 groups, right? Because the 3 children. We used child in order to group the data now. So each group has its separate intercept, you could say. But this output here is new compared to the LM output. The rest is more or less similar. Temporal pseudo-replication. So actually pseudo-replication means you have replicates that are not really independent. Typical cases where mixed models are used a lot is this. Temporal, it means over time. And this is actually repeated measurements over time on the same unit. And what do I mean by unit here? It could be an individual, that's typical in medical applications, right? Where you follow the same person over time and you measure something on this person, the same person, right? But this can also be groups, or it could be, for instance, locations. I imagine if you do some studies of environment, you go to the same forest, for instance, and the same location in the same forest, and monitor how things changes over time, right? Or it could be an animal, or it could be some plants or whatever. But the point is that there is some unit that you repeatedly measure over time. And this is quite common, I think, in many of the research fields at NMBU. Data from the same unit are now similar to each other to some degree, right? Or dependent, as we say. This is not always the case, of course. So, and this varies from being almost independent to be strongly dependent. So it's not like this setting needs always a mixed model approach, but it depends on this dependency. This is also sometimes called longitudinal data because it sort of tracks the same unit over time. Longitudinal data, yeah. Repeated measurements on the same units are what we call the pseudo-replicates here. It's not real replicates because they are made on the same unit. You can imagine an extreme example of this. Let's say we wanted to measure the height, or investigate the height of girls and boys at a given age, say 6 years of age when they start school. And then you would, for instance, go out and measure 100 girls and 100 boys, right? In order to study, is there a difference in height at this age, right? 6-year-old children. Another way of approaching this would be to, instead of measuring 100 girls and 100 boys, is to take 10 girls and 10 boys and then measure each girl and boy 10 times. Then you also get the same number of measurements. As if you measured 100 girls and 100 boys, you have 200 measurements, right? But you have measured the same girl and boy 10 times. And of course, these measurements are not identical, right? Because there is always a slight variation in measuring height of a 6-year-old child, right? So you will not get exactly by the nanometer the same value each time, but it's almost the same, right? And these are pseudo-replicates, right? If you now come to R and say that I have 200 measurements, no, you don't. You don't have 200 independent measurements. You have made 10 measurements on each person, right? Which is only almost the same as one measurement because it's the same thing you measure over and over and over again. So that's an extreme case of pseudo-replication. When you do this over time, it's a little bit of the same, right? Because you track the same unit over time, so you expect that the next measurement will be quite similar to the previous one. But of course, it depends on the time scale here and what has happened in the meantime. But this is pseudo-replicates. We are not really interested in the difference between each unit. If that's the case, sometimes we are. But in this case now, We are not really interested in the difference between each unit, but we rather see them as a random sample of a larger population of such units. Right? So again, the medical case, when you track patients over time, it's not in this setting because you are interested in these particular patients, but you are interested in them as a representative of a much bigger group of people, right? Or it could be that you are sampling in a location in the forest, but you're not really interested in that particular location. You only see it as a representative of all the locations you could have sampled from, right? And then you have a random sample from a larger population, and the effect of the unit is then typically a random effect. And regression with random intercept or random slope is what we will look at here now, because we typically have some fixed effects, especially time in some sense comes into the picture as a fixed effect, but could also be other fixed effect. But in addition to that, we have this random effect of the experimental unit, either being a person or a location or a plant or an animal or whatever. The fixed effects are what we are interested in these type of model typically, right? We want to see what happens over time, right? And if we have, for instance, in the case of the medical, if you have testing a new drug, right? You have some people who get the drug and some who don't, right? And you're interested in seeing what happens to these over time, right? And then you have the fixed effect of time and the fixed effect of drug, because drug is not a random thing. That's what you are focusing on, right? So you have some trend over time, and you typically have some effects of some treatment or whatever affecting this trend or the intercept, right? And we test, as usual, these regression coefficients. Are they zero or not, right? Is there an effect or is there no effect? The random effects in this type of models are noise. We're not really interested in the random effects, but they must be included because they describe how the data set should be analyzed, you could say. They describe the structure in the stochastic elements of the data we have collected. So their standard deviation may be interesting in the sense that if there is a huge random effect, at least it was important to include it. It may also have some implications of how we analyze the data, or in particular how many, for instance, if there is a huge person effect, right? Then we need quite a lot of persons, because we are not really interested in each person's effect. We want to see the average, right, over all persons. And if there is a big variation between persons, we need more persons to get this average stable. So it could be interesting in that sense. But most of all, a better model for the data gives a more stable estimates for the fixed effects. And we actually saw this already in the previous example of the reading data, where we got, by adding the random effect, first of all, we got the positive slope. The effect of age was positive on the reading abilities, not negative. And it was also significant. And that's perhaps a little bit surprising, that adding sort of more variance terms to a model gives you more significant fixed effects. But that's frequently the case, because you have a better description of your data. You can estimate all parameters more exactly, stable estimates. So let's go back to R and do some fitting some mixed models to data with pseudo-replication. Let's have a look at this fertilizer data. So this is a data set actually from the R book that we can load, but we have it in our R package, so we can actually load it like this. Yeah, and if you look at the fertilizer data table, This is about measuring the length of roots of plants over time. You can see here week 2, 4, 6, 8, 10. And the third column here is indicating the plants we have measured. So this is repeated measurements over time now of different plants. So these 5 first measurements is from the same plant, ID1, and then the second plant here, ID2, and so on, ID3. So this, the levels of this factor here indicates which plants we measure. And then there are 2 treatments actually. The first plants here have all been grown under fertilizer conditions, and some have not, right? These are the control. These do not get fertilizer. So we have 2 sort of treatments, control and fertilizer, and we track these plants over time. So let's make a figure out of this. And here I show you a way of plotting that I sort of recommend for this type of data. So first of all, we plot the table and we use as x-axis the time column, right? The column that indicates time. And of course the y is the response, the root growth in this case, right? What we are measuring, sort of, right? The root growth and the week. And then I color by treatment. Coloring should always be a factor, and treatment is a factor. The plant is also a factor, but in this case I choose to color by treatment because there are only 2 treatments, right? Only 2 treatments, 2 colors. That looks pretty. How about the last column, plant? Well, we plot each data measurements as a point, of course. We always do that. But in addition, I add some lines, and here I use the plant. I group now the observations by plant such that we draw a line between all the measurements from the same plant. The same level of this factor will now have lines between them. And this is a nice way of displaying longitudinal data. Let me show you. So I run this here and this here. This is how it looks like. And I think this is a really nice way of displaying. You have the time over here in week. You have the response up here, the root growth, the length of the roots. You have the treatments by color, and we can immediately see the difference between the treatments. And also we have these lines connecting the measurements from the same plant. So we can immediately see here that, okay, this plant here, I don't know which one it is, but it was the smallest plant at week 2. It's still the smallest at week 4, 6, 8, and 10, right? And this is a sure sign of dependency, because once you have started measure this one, next measurement will be sort of similar to the previous one, in the sense that it was the smallest plant up here, it will be the smallest plant the next time again, right? If the data were independent, these lines should go up and down, up and down, up and down, right? So that this plant, which is the smallest one and one, can easily be the largest one on the next, and then the smallest one again, right? That would be the case if the data were truly independent. But of course they are not, right? Plants don't grow that way, and longitudinal data are rarely that way. There is a dependency here, right? All the measurements made on the same plant are dependent to some degree. So let's fit a mixed model to this data, and let's start out this way. First of all, what are fixed here? Well, we need a fixed intercept and a fixed slope, I would say, in order to sort of have the regression line over time. That's the sort of the basic thing that happens here. Everything grows over time. And that's a fixed effect, right? Also, I would say that the treatment should be a fixed effect, because we are interested in the treatment, right? We want to test if there is an effect of treatment. And then we have to make it into a fixed effect. And given how this data look like, I think it's sort of fair to say that, okay, the effect of treatment is basically an effect of the intercept here, because the slope seems to be more or less the same for the two. They grow at the same rate, more or less, but there is a difference from the beginning here that could explain this treatment effect, right? So having the treatment as a modification of the intercept looks to me like the most reasonable. We could always modify this, but let's do that now. And then we have some random effect of plant. And so the difference between the plants is now something random. You sample one sort of value, you could say, given that you have plant number X, you sample a given value, and this value is sort of affecting plant X all the way through. But how should it affect it? Well, let's first say that the random effect of plant is a modification of the intercept as well. So that once you start out, for instance, this one here, start out with a large intercept, then it tends to be large all the way through. And this one is the same, right? It starts out with a small intercept. It tends to be similarly small all the way through. So the differences that are sort of created at the beginning stays that way all the way through. So the random effect of plant is modifying the intercept. So we have the sort of grand mean intercept, then the modification due to treatment, then the modification due to plant. And this one is fixed, it's a Greek letter, right? This one is random, it's a Latin letter. Then you have the regression, the slope, right? And the effect, this is time then, or week, right? And we have the error here, which describes the variation within each plant now. Because this one here describes the variation between plants. This is the variation within plants. Both of them are normal distributed, expectancy 0, with different variances or standard deviations. Let's fit the model and see what comes out. And here we fit the model. Let's just briefly look at it, how we specify it here again. The response, yes. And then the predictor variables, the fixed ones, week and treatment, right? And the week is now, so this will sort of, you can think of it as a regression model over week. This is a numeric variable, right? Well, this is a factor. So this is sort of an ANCOVA type of model, but with random effect here. And now we say that the random effect affects the intercept, yes, and it's plant that is the grouping variable. And we can look at the summary of this fitted model like this. And what do we see? First of all, we can look at the fixed effects. Yeah, we have, of course, a huge, or we have a very, very significant effect of weak. Positive, yeah, that's obvious, right? Every root grows by time. So there must be a very positive slope here. And highly significant, because all of them grow, right? The effect of treatment, fertilizer, used to control as the reference here now, because that was the first factor level. And then we can see that going from control to fertilizer means we add something to the intercept. And that's also reasonable. We see that all the blue ones are above the red ones, right? The fertilizer are in general longer than the control roots. And this is also highly significant, of course, because there are there are some overlap here, but for the rest, all the blue ones are above the red ones. The random effects, here we have their standard deviations. So we can see that this is now the standard deviation between plants, while this is the standard deviation within plants. And they are, well, more or less of the same magnitude, I would say. A little bit bigger, this one, than over here, but approximately of the same magnitude, which means both of them are sort of contributing with equally much, or almost equally much, to the total variation. And it also means that the correlation between plants, between measurements of a plant, is roughly 1/2 or something. Yeah, you can actually compute it. I don't do it. It's less than 1/2, but yeah. So the actual correlation between measurements on the same plant is not super big, but it's not super small either. From this output here. Okay, let me show you some plots that could be very interesting to make here now. And something you in principle always should do, I think, when you have fitted a mixed model. First of all, here I take the data set and I mutate in 2 new columns with the fitted values for the fixed effects and the random effects. So here we have the fitted model object. If we open that, it's here, I think, there it is. Yeah, you can see that inside this there are lots of things, but here is fitted, right? You can see that. And this is actually a matrix with 2 columns. So if we have a look at it, if I copy this one and take it out here in the console, if we have a look at this one, you will see that this is a matrix with 2 columns. The first one is the fixed effects after, the fitted values for all the fixed effects. And here we have for the random effects. So I add this to the table. So if I just put this into a dummy variable here and run only this code, we can always have a look at this TBB. Oh, there it was. We have the original data plus this fitted values added, right? And then instead of storing it, we put in a pipe operator again. Then I just pipe this into ggplot, and again I plot. How do I plot? With time on x-axis, root on the y-axis, and I color by treatment. So this is the same dots as you saw here, but now I add line with, again, time on x-axis, but now the fitted fixed values instead of the raw data, right? Again, I color by treatment, and I group by plant. And notice this is a thick line because it has size 2. And then I add the same, but instead of the fixed, I use the random effect fitted. And what is the difference here? The fixed effect is the same now for each plant for the same treatment. So even if this one plots many lines, most of them will be on top of each other, because the fixed effects for the plants of the same treatment are the same, but the random effects are not. So this here will result in many different lines, and that's why I set line type 2, because this means a broken line. So let me run this now and we will see this. Here you can see the output. So now this is sort of the model prediction of our data, you could say. A thick blue line here is the sort of the fixed effect of so this is, you can imagine this is sort of the average plant given treatment and fertilizer treatment, and this is the average plant in the control group, the thick lines. And then you have the thin broken lines. Those are they describe the variation between the plants, right? The normal distributed random variation between plants. But you can see that for a given plant, you have a straight line, right? because it's sort of parallel to the corresponding thick line, but it has this random intercept, right? So it describes the variation around the data. A figure like this could tell you if the model you have fitted is sort of sensible, or I call it a sanity check. Because if the predictions here now are wildly different from the points, there must be something dramatically wrong in your model, I would say. Okay, there is another plot as well I would like to make, and that's of the random effects only. Because when we when we fitted this model, we assume that the intercepts has a random element, right? And if we go back to the output, if I scroll back to the here, yes, then we can see the variation in this is the between plant variation, standard deviation, right? This is the standard deviation of the normal distribution that describes how plants differ between each other. And this is the exact value that I have added here. And here I now draw some, I make a normal distribution with mean 0. Remember, this is always mean 0. We assume always mean 0, right, in our normal distributions. Here it has mean 0, expected value 0. And the standard deviation is estimated to be this. If I now plot a normal distribution like this, theoretical one, I can compare it to the actual coefficients for each plant that was estimated from the data. So this one here, what is this one? These are the random intercepts for each of the 12 plants. Right? That was estimated from the data. These should now be normal distributed, right? With mean 0 and this standard deviation here, approximately. And that's what I'm checking here. I have the sort of theoretical normal distribution here with this spread, and now I plot that together with the data to see if that is a reasonable description of the intercepts in our data. So the thick blue curve here now is the theoretical normal distribution having a mean 0 and a standard deviation this big. The gray shaded area here is a smoothed version of these data. You could have made a histogram in the same way, but that's not so pretty when you compare it to a smooth curve like the blue one here. So I use the density here, the geom density you can see here. You can explore this a little bit on your own. But I make a density based on this observed and then compare it to the sort of theoretical. And in this case, it looks very good, I would say. It's only 12 plants, right, behind this gray sector, so it will not be very sort of exactly like a normal distribution because it's only 12 samples. But still, it's quite good, I would say. We can see it has a top here around 0, and it has a spread which is as it should. So this is also a plot for what I call a sanity check. Did you actually estimate some standard deviation that matches your data, sort of? And it looks like it. Yeah. So let's fit another model instead, and where we say that, okay, the random effect of plant is not affecting the intercept, but it's actually affecting the slope. So instead of each plant having its own intercept, all the plants have the same intercept now, coming, or at least all the plants from the same treatment. They have the same intercept, this one, but they have differing slopes. And then we add, now Bj is the random effect. I called it something else so we don't confuse it with the Aj from previously. So now this is a random effect on the slope, right? Because we add this to the slope. So each plant has its own slope now. And that's the only difference really. So let's see if we can fit this model. And of course it's quite similar to the previous one. And the only difference is really here. And this is sort of worth mentioning. So let's have a look at this line of code now. We specify again root as the response, weak as a numeric fixed effect, which means it's a regression model, and then treatment as a factor. So we modify the intercept again by the treatment. That's the alpha, right, in the model equation. But look at the random effect, how I specify this now. I say weak minus 1. What do I mean by weak minus 1? It means weak should now be affected. That's the x, right, the regression predictor. And when I write minus 1, it means but not the intercept. Right? If I had only written weak without this minus 1, then this function will interpret this as random effect should now both affect intercept and slope. So in order to only affect the slope, you have to include the regression variable and then minus 1 to say not on the intercept. But still, it's the same grouping variable. It's still the plant column that gives us the grouping, right? So let's fit this model as well and look at its summary. And what happened now? Well, of course, the effect of weak is still the same. Yeah, we should have made the window a little bit wider. The p-values came on the second, on the separate row here, but you can see it's the small p-values again, and the treatment effect. It's not identical to the previous one, I think. Is it? Yeah, it might be. It shouldn't affect the fixed effects very much, this, because the data are balanced and very nice. So the actual big effect here comes from up here, because now you can see the first standard deviation here is very much smaller now compared to previously, and also this one changed slightly because now we have a different description of the stochastic elements. Now this first one here is now a variation in slope, not in intercept, right? And that's why it's so much smaller, because if you look at the data, the slopes doesn't vary that much, right, between the plants. If we go back and look at we can look at this plot here, you can see that the slopes are more or less the same for each plant. So this should be small, right? This should be small. We can again make the same plots as we did in the previous, from the previous model. It's just more or less copying the same code and just replacing some replacing the name of the model object, right? Instead of mix int, it's now mixed slup. But apart from that, it's the same code really. And now the plot looks slightly different, because now you can see that all the fixed effects are more or less the same, but the random, the dotted lines, the broken lines, they now sort of come from the same intercept, but they have different slopes, so they grow more and more away from each other, right, as time goes. So a random slope will typically describe a case where the different individuals grow apart from each other as time goes, right? So for each plant, we now sample from a random normal distribution a value and add or subtract that from the sort of average slope. So some have smaller slope, some have bigger slope than sort of the average plant. That's what we see here. And again, we can always look at this normal distribution, the theoretical one, like we did in the previous case, and see how the fitted how this compares now to the data. So now I had to copy this value, right, from the output up here, this one. So now it's a much it's a normal distribution with much smaller standard deviation. And if you now look at the random slopes, we can see they match sort of good. It has 3 tops, but that's only because we have only 12 plants, right? If we had like 1,000 plants, I bet it will look very close to this one. So having an assumption of a normal distribution with mean 0 and this variance is not a bad assumption given these data, I would say. So this sanity check, these 2 plots here, is the fitted model near the observed data? Is there a random effect more or less normal around 0? That's a good thing to do. And then let's finish by having this model here where we now have both random slope, random intercept and random slope. Couldn't we do both? Of course we could. There could be both a plant-specific intercept and a plant-specific slope. Both of them random variables with some standard deviations. So here's the code for doing it. And now you will see we get some problems here. If I try to run this code, fitting a mixed model with both. And notice now, I now specify in this term here, random, and I say weak without weak minus 1. And that actually means let the random effect affect both the slope and the intercept. But if we try to fit this model now, we get an error. And this is something I would like to show you, because you have what is called a convergence error code 1 here. So iteration limit reaches without convergence. What does it mean? It means that when we try to fit the model to the data, it doesn't find a solution. And this is typically the case if you try to fit a too complicated model to a smallish data set. And this is actually the case here, because there is not enough observations to both fit the slope of time, right? The treatments for the groups, and all a random effect of slope and a random effect of intercept. All this requires so much information that we don't have that much information in that data set. So it's really not possible to do it. And it's clearly an indicator that this was a too complex model. It's an attempt to do an overfitting, you could say, but we couldn't even overfit. It terminates before we can even fit the model to the data. So it happens, of course, if you don't have big enough data sets and you try to fit a too complex model, this will happen. So it's not an error in R or in your code. It's simply that you are trying to do something which is not possible to do, you could say. So to overcome this, you need more data, actually. And I have to say that in the weekly exercises, you will have a look at the similar data set which is bigger, and then you can do this. So I will leave you to do this in the exercises. So a few words about model fitting and model selection. So the maximum likelihood approach is something we could use to fit a mixed model. And that follows from the assumption of normal distributed data. We have some assumptions of all the distributions here. And when we can always, at least in theory, use the maximum likelihood principle and fit the model to the data. I talked a little bit about this in the very first week, but we will not dig into how to do the actual maximum likelihood fitting, because that's sort of a complicated numerical procedure, at least in some cases, and in this case it is. But the maximum likelihood as an idea is at least available here. However, there are some problematic instances here. Because we have multiple stochastic terms, we can actually end up having negative variance estimates if we use maximum likelihood. That happens sometimes. It sounds strange. How is that possible? Well, it is possible. The estimates that maximizes the likelihood function produces negative variances, and that is of course insane, right? A variance cannot, in theory, be negative. But data can be such that this comes out as the best estimate. So in order to avoid this, because it makes no sense, right? There is a different approach called the restricted maximum likelihood, shorted REML. And this is the default way of fitting mixed models. It avoids these negative variances, but it doesn't produce the same result as maximum likelihood. In normal cases, this is fine. We are satisfied with the REML estimates, but there are some cases where we want to have the maximum likelihood estimate anyway, regardless of this potential problem here, right? Because this negative variance is not something that happens all the time. It only sometimes happens, right? So the default is to use this REML, but we may specify that we want to use maximum likelihood, so sort of forcing the R function to do it this way instead. And this is something we will do because it has to do with the variable selection. So mixed models, just like any other linear or generalized linear models, may be either too simple or too complex given the data set. We can underfit the data set, meaning that we are using a too simple model and there are effects that we don't estimate, or we can use a too complex model and overfit to a data set. So this is exactly the same problem as we have seen before, right? Mixed model is no different from other models in this term. So from week 2, we saw one way of doing a variable selection using what is called the Akaike's information criterion, AIC in short. And this one, in order to use this criterion for choosing between different models, you have to have a maximum likelihood estimate. You have to have fitted the model using the maximum likelihood approach. And this is why we need, as in the previous slide, sometimes to sort of force the R function to use maximum likelihood instead of this restricted maximum likelihood, because we want this AIC criterion for our model. So now if L is then the likelihood function and L hat is the value it gets at the maximum likelihood, we saw this in week 2, you can look back and see, then we have the Akaike's information criterion is simply 2 times P, which now is the number of parameters, minus 2 times the natural logarithm of this likelihood value. So this is simply a number. AIC is a number, right? So P is the number of parameter, number of fixed effects, and number of standard deviations or variances in our model. And the model having the smallest AIC fits the data best. That's the rule. So if you want to sort of compare models of different complexity, a simple, medium, complex model, if you want to compare them, which one of them fits the database, this is one way of doing it. It gives you sort of the best balance in some sense between under and overfitting. So the model getting the smallest AIC is the one to prefer if you use this. I mean, this is only one criterion. You could have used some others. And next week we will have a look at an alternative approach. But this is one way of doing it. And let's have a short look at this now. Because this AIC is a typical output from this mixed model. So it's there for us to use if we want to. Okay, let's round this off with an example of spatial pseudo-replication, which is almost the same as temporal pseudo-replication then, right? But instead of repeated measurements of a time, we may also, of course, have repeated measurements of a location. So the measurements are done at more or less at the same time, but almost at the same place. And that also introduces dependencies, right? So in a regression setting, this results in similar random intercept, random slope considerations. So I will actually now have a look at this other example, which is also from the R book, with plant and nitrogen measurements, plant growth and nitrogen measurements from some farms. Well, let's finish by this farms 0 data. And actually in the R book, the data set is called farms. This is a subset of that data set. Yeah. You can read a little bit about it here. I will not go through that. It's basically measurements of soil nitrogen and plant size from different farms, right? So we are actually interested in if plant size is affected by nitrogen, and then several measurements are made on the same farm, and there are many farms, 24 farms. So let's load the data set and do some plotting right away, right? Load the data and plot it here. And notice how I plotted now. I plot X as nitrogen and Y as plant size, right? Because these are sort of the two variables we are most interested in. Is there effect of plant size from nitrogen, right? Sorry, effect of nitrogen on plant size, right? This is the response. And again, there is no sort of treatment here, right? So all the colors are the same, but I use the same idea as before, because the measurements from the same farm are now being sort of linked by these lines. So each observation is a dot, and those who come from the same farm are now linked. So you can see these 4 measurements here are from the same farm. These are from the same farm. These 2 from the same farm. So it varies. Some farms have 5 measurements and some have only 2. I think there is no one. Yeah, there's only one here. There's some farms with even only 1 single measurement. And that's the difference to the big data set where all farms have 5 measurements. But what we can immediately see here is, of course, the huge difference between the farms. Not in terms of nitrogen so much, perhaps, even if this farm here has clearly a lot of nitrogen compared to this farm here in the soil, but the plant sizes are hugely different, right? Some farms have only small plants and some have quite big, even at the same nitrogen level. So, and actually the farm is not now of real interest to us, because these 24 farms are, we consider just a random sample of 24 farms from all the farms we could have visited, right? We are not interested in these particular farms, but we are interested in the effect of nitrogen on plant size. So if we just fit a standard normal sort of standard regression model here without specifying anything about dependencies. We say, okay, let's fit the linear model with plant size as response and nitrogen as the predictor variable, right? And then look at the fixed model output. You can see that, okay, there is an estimate of a positive effect of nitrogen, but it's not significant. So you can imagine there is a sort of a weakly positive regression line here, but the variation is too big for this to be significant. Even if we have 78 degrees of freedom. Because now we say that we have all the data, all the 80 data points. There are 80 data points in this data. All the 80 observations are independent of each other. So it means we have 78 degrees of freedom. Not enough, because the variation is so big, right? The standard error or the residual standard error is huge, 9.1 more or less. So, of course, we should fit a mixed model here, and again we use a mixed model with a random intercept, because I mean when you look at this data, this is the natural thing. For each farm, there is sort of a new level, you could say, right? That's what this random intercept means. So we now have a random effect of each farm, which we add as a modification of the intercept. And then we fit this model, of course. And you can see it's the same fixed effects, but now the only difference is we say this. Okay, there is a random effect of farm that should affect our intercept. And if we fit this one now, we can immediately see that the effect of nitrogen is, first of all, it's bigger than before, because here it was 0.3, now it's 0.8, and it's significant as ever, right? And notice that we have fewer degrees of freedom now because we have a more complex model, but the standard error for nitrogen is super small, because now we have this standard deviation, right? The farm effect is huge, right? And that has nothing to do with nitrogen affecting plant size. The farm effect is effect of farm, of location, right? And that is now sort of taken care of by this term. That's why we can have this very small variation here now. So this was a very, and I mean, if you compare this standard deviation to this one here, you will see that, and you compute this correlation, we can actually do that again. What was this one? 8 point, copy this one here, squared divided by this one squared plus, what was the residual? This one squared. Yeah, you can see 0.95. It's a huge correlation between the measurements of the same farm. And that's not surprising when we see this plot. If you sort of want to know which plant size you have, there is the information about which farm you are at is the most important one. The nitrogen level is not important compared to which farm are you at, right? That's the one that gives you the most information about the data. Okay, we can always do this sanity check again that we did before for this fitted model. I think this is a good idea. Yes, there was an error in the code here. It should be farm 0, not farms. There you have it. And here we can now see how the the black dots are the data as before. I don't have the lines that connects them anymore, but now instead we have, this is the, sort of the main effect of nitrogen on plant size, right? The big thick line, and here we have the sort of the fitted values for each farm now as the broken lines. So this looks, yeah, pretty nice, I would say. You can see that the big difference is between the farms, right? So this sanity check is always worth. Then I would like to mention, in the R book where they talk about this example, they actually fit a strange model. And that's this I mentioned just to show you that textbook authors are not always the best teachers. What is this model fitted here? Look at this. Here we have the plant size as a response, yes, and nitrogen, and then farm as a fixed effect. So this is actually this ANCOVA model, right? Sorry. Where we for each farm now have a separate intercept. And then in addition, there is also a random intercept for each farm. I mean, isn't this completely crazy? I mean, you cannot both have the fixed effect of farm and then a random effect of the same farm. The point is that you can actually have this when it comes to fitting the model, because if I run the model fitting here now, it works fine. And the summary output, let's have a look at it. Yeah, you get some warnings here. I'm not surprised, because if you now scroll back up here to the fixed effects, look at this. The p-values, none. And that's because you have 0 degrees of freedom. I mean, this is, if this isn't overfitting, then I don't know what overfitting is, because here you try to fit both a random and a fixed effect of farm, and you have only like, you cannot expect the same farm to be both sort of random and not random. But I mean, technically it's possible to fit a model like this, but this makes no sense. This is pure rubbish, I would say. Pure rubbish. Don't do this. That's my conclusion. What I would do at the end here is to just show you how we can use this Akaike's information criterion. So now I have, just from having 2 models to compare, I now fit first a model where I don't have this effect of nitrogen included. So you can see plant size is now simply affected by the intercept. This means no, this is sort of a regression without the predictor, right? So everything is flat, you could say. It corresponds to these lines being flat. But we still have the random effect of farm. So there will be the intercept will have a random component depending on the farm. And then I also use this method equals ML to force a maximum likelihood fit to this using this model. So if I run this one first, this fits this first model, and then I just extend the model by including nitrogen as a predictor. That's the only difference now, right? The rest is exactly as in the previous model. So if I fit this one now, I have a second model here. So now we have 2 models, alternative models for the same data set, right? This is the simpler one. This is the more complex one, even if I wouldn't say any one of them are particularly complex. But this is just for showing how to approach it. And then we can do this to compare them. And then you always list the simplest model first, and then the more complex one afterwards. So if I run this one now, and over here, you will see, yeah, let me make the window bigger. You will see the 2 models here, and you can have 3, 4, 5 models if you like, but make sure they are ordered from the simplest to the most complex. And then you have the simplest model here, yeah, and here you have the Akaike AIC criterion, right? So now we should just look down this column to see which model has the smallest AIC value. That's the one we choose. So if we had like 3, 4, 5 different models, of growing complexity, we would simply just look down this column here. Which row has the smallest value? That's the model we choose. And in this case, it was no surprise, this second model that comes out the best one. Actually, this is also, instead of doing looking at the t-test like we did above to see that nitrogen was a significant predictor for plant size, we could actually do it from here as well, because we know that the only difference between these two models, going from this model to this model, is to include the effect of nitrogen. And since this came out better, it means that including the effect of nitrogen was beneficial. It made a model significantly better, you could say, according to the Akaike criterion. So that's an alternative way of testing the fixed effect, really. We will talk a little bit more about this next week.